All right, we were just looking at all of the sum of square definitions. And so the sum of squares, so sum of squares measures the total variation in the data. It's just the sum of the squared differences from the mean. That's all we were doing in all of these formulas, right? We're taking differences from the mean. However, to appropriately determine whether the difference in means is due to the factor effect, so the factor effect or randomness, we need to calculate the mean squares. So the mean squares, we're now switching terminology from variation to variance. It's just the sum of squares divided by their degrees of freedom. So the mean squares represent the average squared deviations from a mean. So instead of just looking at the total variation in the data, we're now looking at average deviation in the data for each of the groups. And that's going to give us a much better idea as to where that variation is coming from. Is it from randomness or is it due to our factor effect? To do that, we need to find mean squares. So these calculations we do need to understand, like really understand, because we're going to be responsible for doing this. So let's take a look at mean squares. So mean squares. So the first is mean squares of total variance, so MST, which is just this total sum of squares, divide by n minus 1. So you just take SST, divide by n minus 1, where n, of course, is the number of observations in our data set. Then we have mean squares among group variance. So this is just the average variance across groups. So MSA is just going to be the sum of squares among groups divided by C minus 1. Again, C is the number of factors, or the number of groups in each factor. So in our example, we would have taken the sum of squares among groups and divide by 3, because we had 4 levels of the factor. 4 minus 1 is 3. And then we have mean squared from within the groups. So mean squared within will be the total sum of, or the within sum of squares divided by n minus c. So that would be the number of observations minus the number of groups. So in our example, we had 40 observations in 4 groups, and that would be 36 degrees of freedom for mean squares within variance. So pretty simple formulas. But like I said, we need mean squares so that we can actually get an idea of where this variation is coming from, and so that we can actually calculate a test statistic. So let's discuss our test statistic, which is going to be the F statistic. We saw this briefly in chapter 10. And it is just the ratio of 2 mean squares. So F stat is just the mean squared among groups or between groups divided by mean squared within groups. So it's a ratio of 2 mean squares among groups over within groups. So let's say we get a value close to 1 for our F stat. So values close to 1 suggest that variation is due to randomness. This would support the null hypothesis. Whereas if we have bigger F stat values, so let's say much bigger than 1, this suggests that the variation is due to the factor effects. And this would support the alternative hypothesis. Whereas values closer to 1 would support the null hypothesis. We can think about that, right? Because in a fraction, when the numerator gets bigger, the overall fraction gets bigger. But when the denominator gets bigger, the overall fraction gets smaller. And so that's where if our F stat is really big, then that means MSA must be much bigger than with MSW. But if we get a small F stat, then that means MSW is a lot bigger compared to MSA, and therefore the variation is due mostly to random chance and within variation rather than across group variation. So We're going to want big F-stat values in order to reject the null hypothesis.